Hello physics students. Today you're going to be learning about the Standard Model, which is the most modern physics that you're going to learn in this topic. In fact, the theory was finalized in the 1970s and the work is continuing on the theory to this day. You may have heard a while back of the discovery of the Higgs boson. That's part of the Standard Model theory. So before we begin with the Standard Model, first I want to just kind of review the structure of atoms. You already know this from chemistry class, but what I'm going to do is just kind of look at a helium atom. So a helium atom, of course, has 2 protons and 2 electrons, but also 2 neutrons. As you know from chemistry, the protons and the neutrons are in the middle, in the nucleus of the atom, and the electrons orbit around. Now, from the physics that we already know, you know that the protons, being both positives, are repelling each other. They should fly apart. That means that there must be another force holding them together, preventing them from flying apart. So we're going to learn about that force today. Also, these electrons are pulled inward because they're negative towards these protons, and so that's what allows the electrons to orbit the nucleus of the atom. Also, there's a repulsion between these 2 electrons. I didn't draw them, the repulsion, because I just want to keep this diagram as simple as possible. But before we move on, I just want to point out there's some inaccuracies to this drawing right here. First, the electrons, as we learned in the Bohr model video and in the particle waves video, they're orbiting the nucleus not as little dots of mass like the Earth going around the sun, for example. They're orbiting around as waves with crests and troughs wrapping around in an orbit. Also, electron as a particle, when you do an experiment, it becomes a particle for your measurement. It has no size as far as we know. So I should draw little specks here to be more accurate, but of course then you wouldn't see it. Another problem with this diagram is the scale. The scale is horribly inaccurate. If I were to expand a helium atom, maybe in some kind of special magnifying glass, so that the nucleus became this big, in order to draw this accurately to scale, if everything expanded out equally, these electrons should be 11 miles away. Pretty remarkable. This atom is basically like mostly empty space. And that's not just the helium atom, it's all atoms. So when I touch this here, this chalkboard, basically in the middle of the atoms are little tiny specks of mass that include more than 99% of the mass of the whole atom are in the middle. All around it is mostly empty space, and then you've got the electrons orbiting around. So this is mostly empty space. Even things like steel or titanium or diamond, mostly empty space, even though they're very hard to our perceptions. So then the question is, if this is thrown at my head, why can't I just say, you know what, this is mostly empty space. I'm not even going to bother ducking because it's not going to hurt me, empty space. Well, the reason why it hurts is because my head is also mostly empty space. Everyone's head is, because it's made of atoms. And this empty space hitting this empty space, this just happens to be more rigid in structure, so it will damage my head. So that's why when things seem hard and dense, it's a relative thing of our perceptions, but matter mostly empty. So very interesting. All right, let me create a pause to give you a chance to copy these notes down. All right, so there's a structure to this, and what we're going to find out today is, you know this from chemistry, that atoms can be broken into protons, neutrons, electrons. Today we're going to see that the protons and neutrons can be broken into smaller pieces. The electrons cannot be broken into smaller pieces. That's going to come later. That's basically getting into the heart of the Standard Model. So, but before we do that, I want to review the 4 forces of nature I mentioned this briefly earlier in the topic when we were studying the electrostatic force. I mentioned there were 4 forces in nature. I talked a little bit about it. Of the 4, the strongest by far is what we call the strong force. It holds the nucleus together. That's one thing. So we said, remember I said, well, what keeps these from flying apart? It's a strong force, like a glue sort of keeping them together. And it also holds the protons and neutrons together. So remember I said these are made of pieces. What holds those pieces together? The strong force. It has a short range, 10 to the minus 15th meters. That's less than a billion, less than a trillion. It's a tiny distance. It can't go far. This is why you never feel the strong force, because it can only go within, act within the nucleus. Remember, these are like 11 miles away, so it can't reach out. When you touch the outside of an atom, you're never going to experience the strong force, which is inside the atom, all the way in the center, in the nucleus. Now, remember when we studied the photon, that the electromagnetic force, there's a particle associated with that, with light waves. Well, same thing with the strong force. The particle associated with the strong force is called the gluon. The next strongest force is the electromagnetic. We studied this. Remember, proton, electron, positive, negative attract, plus, plus repel, so on and so forth. We studied that in pretty good detail, big detail. And then the magnetic force, when magnets interact or electric current wires interact, all those effects together are called the electromagnetic force. It's 100 times weaker than the strong force. It holds the electrons in orbit, obviously, but it's also responsible, as I said all the way back a few months ago, for all 5 senses. Sight is electric and magnetic fields going into your eye, light, okay? Sight, touch, when you touch this, you're touching the electrons in your hand, are getting close to the electron of whatever you're touching. Touch. Taste is charges of molecules hitting your nerves on your tongue, making a sensation. Smell is a similar thing in your nose. And hearing is the air atoms colliding, electron to electron repulsion with your eardrum. So that's all 5 senses, the electromagnetic force, a big force for humans. And the particle is obviously the photon. The next weakest force is called the weak force. It's like 1,000,000 times weaker than the strong force, 10 to the minus 6, contributes to nuclear decay. So it's also in the nucleus. We never feel the strong force because of its short range. Short range here, 10 to the minus 18th, even shorter range than the strong force. And the particle is the W and Z bosons. And then the last one, the weakest by far, is gravitational force. 10 to the minus 39th weaker. Again, there's not even a word for that. But the interesting thing about the gravitational force is, since it has an infinite range like the electromagnetic force, and it never repels, even though it's the weakest, if you keep adding more and more mass, like in a black hole, it becomes by far the greatest of all forces. So powerful it could crush all matter down, and even crush space and time, crushed down by gravitation. So an amazing, interesting force, how weak it is, and then it becomes the most powerful when you add enough mass. So let me create a pause to give you a chance to copy these down. Okay, so moving on, I've got to make some room, and I'll write out the next batch of notes. Okay, so smallest parts of an atom. One is the electron. It cannot be broken down as far as we know. You smash 2 electrons together as hard as you can, and they will not break into pieces. And the violence that they've crashed electrons together with is enormous. They have these things called particle accelerators. You've probably heard of them. They have some in Europe, some in the United States. They're like a ring that's miles across. So imagine a machine that's miles big, and it has giant magnets to keep particles spinning around. And so you have this miles big machine that's powered by power plants that maybe could feed a whole city, and they put all that energy into one electron spinning around and another one spinning around, and they crash them together and they don't break apart. So enormous, nearly infinite energies on the scale of an electron, and they don't fall apart. But if you do that with protons and neutrons, they smash into pieces. A proton breaks into 3 pieces. This is an up quark, and down quark. Just jot those down for now. I'll show you, I'll explain more what those are. Neutron breaks into 3 parts, 3 pieces, also 3 quarks, an up quark, and then down quark, down quark. So those are the compositions of the protons and the neutrons. So let me create a pause to give you a chance to copy this down. All right, so this is basically getting into the standard model. So let me make some room. So I'm not going to write out the standard model because it's in your reference table and I don't want to make this redundant. But let me show you what's there. So before I show you what's there, I want to just kind of call your attention to classification schemes and how they work. Now, there's biology where they classify all the lives. This is too complicated. I just wanted a quick classification scheme so you could kind of see and review how they work. Let's suppose I want to make a classify all writing tools. I can separate them as some using solids and some using liquids to create the writing. Liquids, within liquids I've got pens and markers. Solids, I've got chalk and pencils. So this is a way to just sort of organize writing tools into like a logical classification scheme. Well, as I said, biology has one for life, but physics has one for the particles of the universe. So remember this page with the energy level diagrams below that? You can see classification of matter. That's kind of like that tree that I just mentioned. By the way, this isn't complete. There's more to this, but this is the part of the Regents that's the part that's included in the Regents curriculum. So we've got matter. It can be broken into 2 parts. Leptons, which then cannot be broken into pieces. And then hadrons, there are 2 kinds of hadrons. There's baryons with 3 quarks, like the proton and neutron. And then there's mesons, which are made of a quark and an antiquark. What's an antiquark? Well, I'll explain in a little bit, but basically that's the structure. So protons are a kind of matter, they're a hadron, and most specifically, they're a baryon made of 3 quarks. Now, what are leptons? Well, over here, you can see 6 leptons listed. The electron is one kind of lepton. And notice it has a charge. The charge is listed here as -1e. The symbol for it is E. Okay? And then there's also like the electron neutrino, all these other ones are other kinds of leptons in the family of electrons, things that cannot be broken into smaller parts. The quarks over here, you see 6 of them listed, up, down, charm, strange, top, bottom. So these are more modern names than some of the other things like Isaac Newton or whatever. It might be more Old English, or Galileo is Italian. So these are just, more standard terms. Now the symbols are, as you see, up, U, D, C, S, T, and B. And the charges of each, the up quark has a charge of +2/3 E. So E is 1.6 times 10 to the minus 19th. You would multiply that by +2/3 to get the charge on the up quark. For the charge on the down quark, you would multiply by -1/3, or in other words, divide by -3, divide 1.6 times 10 to the minus 19th by 3. So this is where you find the matter of the in the standard model that we use for various applications. So, but I want to point out some things. The elementary particles, first of all. In other words, the ones that cannot be broken down, we have quarks and leptons. Okay, elementary particles. The composite particles, in other words, the ones that are made of other pieces, okay, so as I said, elementary particles made of quarks and leptons. The composite particles are hadrons, two kinds of hadrons, a baryon made of 3 quarks, like for example the proton and neutron over here. And then there's also mesons, which are made of a quark and an antiquark glued together with a strong force. Now, what did I mean by antiparticles? So antiparticles, also something interesting you're going to learn within this topic, is that an antiparticle is, well, let me write it out and then I'll explain. Fascinating thing, antiparticles. Basically, they have the same mass as the particles. So, like for example, I'll write it down in a second, but you could have a proton and an antiproton. And so it has the same exact mass as the proton, but opposite sign, it's actually got a negative charge instead of a positive. And when it touches another proton, both of them disappear forever. In a little explosion, releases energy or photons. So let me write out some examples here, but let me make some room first. So of course I will write examples over here, but I ran out of room. So let's suppose we have a particle and its name, its symbol is A. So we say A, the antiparticle of A, we would say, we would just put the word anti in front of the A and say anti-A. And we would write that as a symbol like this. We would put a bar over A. That means it's the antiparticle of A. So any particle, put a bar over it. That's the symbol for the antiparticle. In other words, you could have like a proton with a symbol P. The antiproton, P with a bar over it. You could have an up quark. Symbol is U. So you would say the antiparticle has anti-up, and you put a bar over the symbol U. That means when people see that, it's an antiparticle. So the only exception to that, it's very easy. You just put anti in front of the name, anti-neutron, anti-up, anti-down. The only exception is the electron. Symbol is E. So we do not say, you call that a positron. The reason why is historical, but but if you call it an anti-electron, I suppose no one's going to mark you wrong. Maybe they will. I don't know on the Regents. Just know that the only exception to the anti scheme is the electron. Positron is what we call it. All right, so let me create a pause to give you a chance to copy these notes down. All right, the next thing that I'm going to do is just a few examples to show you the kinds of calculations you might have to do with the standard model using that information on the reference table. But first I have to make some room. So there's the example. We want to determine the charge on a proton in terms of E and in coulombs. All right, we already know the answer. It's 1E, positive 1E, and that's plus 1.6 times 10 to the minus 19th. But suppose we didn't know that. We could figure that out. And also what has to be given to you is the Quark arrangement. So you don't have to memorize that. So that'll be given in the problem, the Quark arrangement. This is how you'd figure out the charge. So what you would do is you would go to the reference table and find the charge on an up quark, find the charge on the down quark. So I'll come up here one more time here. So you see, right here, the up quark has a charge of plus 2/3 e, and the down negative 1/3 e. So we've got two of these and one of those. And we're just going to sum that up. So up, down is plus 2/3 e plus another 2/3 e plus a negative 1/3 e. When you add those up, plus 2/3 is 4/3, minus 1/3 is positive 3/3. Well, we don't say that. We just say plus 1e. And of course, we know what E is on the reference table. We could go to the front cover here and find one elementary charge, lowercase e, 1.6 times 10 minus 19th. So we've got positive of that. So the charge in coulombs, 1.6 times 10 minus 19th coulombs. All right, let's do another example. Maybe I'll do it over here. So let me create a pause to give you a chance to copy this down. All right. So here's the example. Determine the charge on a neutron if its quark arrangement is up, down, down. Again, we know the answer. It's 0. It's a neutron, right? But suppose we didn't know that, but we knew it was made of those quarks. So we would find the charge in this manner. We would say Q equals, remember, I'm not going to bring the reference table to this to the camera again, but we've got plus 2/3 e for the up quark. You look that up on the reference table. The down, if I were to show you on the reference table, well, I got over there, is negative 1/3. And I've got two of those, right? That's that one. The second one, the second down one, negative 1/3. And when I take 2/3, add negative 1/3 and negative 1/3, I get 0. So I can say the neutron, its charge is 0. Okay? Now, I just want to point out that you do not have, as I said, you do not have to remember that this is a neutron and that's a proton. However, they may ask you what the quark configuration of a proton is. In a multiple choice, they may say, what's the quark configuration of a proton? And they give you a bunch of choices. Up, down, down, up, down, up, down, down, down. I don't know, I'm making stuff up. But what you would do is you would sum up and you would find that this has a charge of 0. This has a charge of plus 1e. This has a charge of plus 2e. And this has a charge of negative 1e. And so that's how you would figure out that this is the quark configuration of a proton. Figuring out the charges of all the choices, and the only one that comes out plus 1e will be your answer for the quark configuration of a proton. Or you could ask, what's a neutron? You do all this and you find which one is 0, okay? All right, so let me create a pause to give you a chance to copy this down. One more example. All right, so now we're going to figure out the charge of the pion meson. Remember, in this scheme, we saw that hadrons, there's baryons, mesons. Mesons are made of a quark and an antiquark. Now remember I said, well, when a quark touches an antiquark or a particle touches an antiparticle, they annihilate each other. Well, not in this case because we don't have a down and an anti-down touching. Then they would just annihilate each other. But an up and an anti-down, they could bond together through the strong force. We're going to figure out the charge on this particle. So we would do the same thing. We look up the up quark, plus 2/3 e. But then what about the anti-down? Well, let me come to the camera again. So I already looked up the up quark right there, plus 2/3. The down quark, negative 1/3. Well, the anti-down is the opposite sign. So it's like negative 1/3. And so I would write like this maybe, negative 1/3 E, which then makes a positive. When I add this plus 2/3 plus positive 1/3, I get positive 3/3 E, which is, again, plus 1E. So that's the charge in terms of E. And then the charge in terms of coulombs, because E is 1.6 times 10 minus 19th, multiply that by positive 1, I get there. All right, so let me create a pause to give you a chance to copy this down. Okay, that is the Standard Model. So again, a recap. You already know from chemistry about how the nucleus and atom is made of protons and neutrons, and the electrons are orbiting on the outside. But what's new is that in the nucleus, the protons and neutrons themselves can be broken into parts. And so we need to be able to catalog all the forces that are involved in holding this atom together. That was the 4 forces in nature that I talked about. The primary ones are the strong force, holding not just the quarks together to make protons, the quarks together to make neutrons, but all of that together to make the whole nucleus. That's the strong force inside the nucleus only. And then the electromagnetic force also plays into play with all the opposites and like charges interacting. So you need to know all that about the forces, the main concepts. And then you need to know the Standard Model, how to use this information on this page of the reference table to figure out the charges of any quark combination. And you also need to know some concepts about what a meson is, what a hadron is. The table will help you to answer those kinds of concept questions. So that's the Standard Model of physics. I hope you enjoyed this actual modern physics today, and I hope you enjoyed the video. I'll see you in the next physics video.